DC electric motors have a very wide range of applications. You often encounter them in everyday life. They are used in household electrical appliances where rotary motion is required. These include, for example, hair dryers, fans, children's toys, blenders, and many other devices. Electric motors are also used in industrial production, where rotation in different directions is required. How does a DC electric motor work? In this video, we will take a detailed look at how such a motor works, using 3D graphics. Electric motors use the principles of magnetism and electric fields. What causes an electric motor to rotate? Let's look at a simple magnet. It attracts metal objects. Why does this happen? A magnet has poles, north and south. This is conditional. A magnet consists of small magnetic domains that are arranged so that their fields are oriented in one direction. Therefore, it attracts other metal objects. What happens if another magnet is brought close to the magnet? The same poles of the magnets will repel each other. Opposite poles of magnets will attract each other. This is what a magnetic field looks like, conventionally speaking. This amazing property of magnets always works. It cannot be turned off. That is why this magnet is called a permanent magnet. Magnets have another interesting property. If you cut it in half, you will get two magnets, each with its own poles, and both magnets will have the same magnetic properties. Only now there will be two small magnets. And if you cut these magnets in half, you will get four even smaller magnets. The strength of these magnets will, of course, be less than that of the original magnet. Now, let's say this magnet is attached to a rotating axis and can rotate freely. If you bring another magnet close to it, the same poles of the magnets will repel each other, and the opposite poles will attract each other, and therefore the magnet attached to the axis will turn. And if the unattached magnet is turned so that the poles change places, the magnet attached to the axis will turn again. Thus, by changing the poles on the unattached magnet, it is possible to force the magnet attached to the axis to rotate. Now let's consider what function electricity performs in an electric motor. Let's create an electrical circuit. Suppose we have a battery, an electrical wire, a fan, and a switch. We close the circuit and electric current flows through the wires, just as water flows through pipes. The fan will spin. This will continue as long as the circuit is unbroken. If we break the circuit using the switch, the electric current will stop. The fan will stop spinning. Close the circuit again and the fan will start spinning again. In this case, the electric current flows in one direction. The fan also spins in one direction. If you turn the battery upside down, the electric current will flow in the opposite direction, and the fan will rotate in the opposite direction. Electric current also has magnetic properties, just like a simple magnet. And the direction of magnetic fields can be determined by the right-hand rule. If you take an electric wire in your right hand, wrap your four fingers around it, and straighten your thumb will point in the direction of the current, and your other four fingers will point in the direction of rotation of the magnetic field. This can be explained more simply. Imagine that you are screwing a right-handed bolt into a nut. The translational motion of the bolt will be the direction of the electric current, and the rotational motion of the bolt will coincide with the direction of the magnetic field. Now let's twist the electric wire into a spiral and run an electric current through it. The electric current will create an electromagnetic field in the coiled turns. The result is a magnet, an electromagnet. It has the same properties as a simple magnet. This electromagnet will also attract metal objects and also has poles, north and south. But this magnet has a difference. It can be turned off by interrupting the electric current, and it can be turned on again by letting the electric current flow. If you change the direction of the electric current by turning the battery upside down, the poles of the electromagnet will change to opposite ones. It is this key difference that is used in a direct current electric motor. Now let's take a simple metal rod. For example, a bolt. It is not a magnet, but it also has small magnetic domains. This bolt does not have magnetic properties because the directions of its magnetic domains are randomly arranged. Let's run an electric current through a circuit with a spiral wire and insert the bolt into the spiral. The magnetic domains in the core align in the direction of the external field, creating their own strong magnetic field, which adds to the field of the coil. The result is a much more powerful electromagnet than the coil itself with current without a core. Let's assume that this electromagnet is attached to a rotating axis and can rotate freely. Bring a permanent magnet close to it, and the electromagnet will rotate. Change the poles of the permanent magnet, and the electromagnet will rotate again. As you can see, the electromagnet rotates, but the electrical wire also twists. We need to change something in the design. The ends of the electrical wire need to be made shorter. The rotation shaft of the electromagnet needs to be lengthened. Add a commutator. This is a ring with slots. The commutator will rotate together with the armature. Add brushes. The brushes will slide along the commutator ring. Springs are installed in the brush housing to ensure constant contact between the brushes and the commutator ring. Current will flow through the wire, brush, commutator, spiral winding, and back through the commutator, brush, and wire. Bring permanent magnets close to the electromagnet. It is better if these magnets are of a different shape. The magnetic fields will interact, and the electromagnet will begin to rotate. As the armature rotates, each segment of the slotted ring comes into contact with one brush. But when the armature turns completely under the influence of the fields, the segments of the slotted ring will come into contact with the opposite brushes. The electric current in the armature winding will reverse direction and the poles of the electromagnet will switch places. Thus, by changing the direction of the current, the armature will rotate as long as there is electric current. If the current is interrupted, the armature will stop rotating. However, such a design, with a single electromagnet, may operate unstable, especially at the moment of switching the current to the opposite direction. Let's add another identical electromagnet with commutator segments to the design. Now, when both magnets rotate, the electric current will change direction as the commutator segments come into contact with different brushes. Accordingly, the poles of the electromagnet will also change places. Let's close the circuit and turn on the electric current. In this design, the rotation will be stable. If more turns of wire are added to the electromagnet, its magnetic properties will increase and it will rotate faster. The more powerful the electromagnets, the faster the armature will rotate. Let's take a look at an electric motor. It has a stator. These are permanent, immovable magnets. They are located on the sides, along the body of the electric motor. The body also has brushes for contact with the commutator ring. The brushes are immovable. They mechanically switch the winding segments, thereby ensuring the rotation of the rotor. The motor has a rotor, also called an armature. These are electromagnets with commutator ring segments, the moving part of the electric motor. They rotate and switch the direction of current in the armature winding segments. This design of electric motors is widely used in robotics, household appliances, automotive electronics, children's toys, and many industries.